Ignacio from Instituto de Física de Plata, and he will tell us about irreversibility, QNEC, and defects.
Okay, thanks a lot for the invitation to speak here. I'm going to talk about this paper I did in collaboration with Horacio Cassini and Gonzalo Torroa. And also, if time permitting, I will tell you about some work in progress that is also in collaboration with Nicolás Abate and Gonzalo Torroa. They are in Bariloche. So the main question I will try to address in this talk will be related to the fact of the reversibility of the Archie flow. The idea is very intuitive and has many applications in physics. And basically what it says is that as one runs along the Archie flow, one decouples from the UV degrees of freedom, and basically you cannot flow back, basically. So the Archie is irreversible. And the idea of irreversibility theorems is to make quantitative statements out of this sort of intuitive idea. And how they work, you basically have to do two things. First is to identify what are the Archie charges that partially characterize the fixed points, and then show that they decrease along the Archie. There are different levels of strength that you can prove these things, but the most basic statement, what it says is that the Archie charge in the UV should be greater than the Archie charge in the IR. Okay. So what I will be speaking about is the two main directions where irreversibility was proven. First, for relativistic quantum field theories in D equal 2, 3, and 4. And then for defect quantum field theories in the small d equal 1 to 4 and big D greater than 5. Basically, what I'm speaking in this second line is to consider a planar defect embedded with little d dimension, embedded in a big D dimensional CFT. And the idea is that the defect is conformal in the UV, and we turn on some relevant deformations, but localized only on the defect. So basically that's what this operator is trying to say. This is referring to the UV fixed point theory, and then you deform it by something that only runs along the small d directions of the defect. And then we are assuming that it will flow towards an IR fixed point, but the bulk does not flow. So
you're assuming the bulk doesn't flow, or I mean, you can show in examples that it doesn't, but is it an assumption of what you're doing that it doesn't?
Well, it's something that we don't know an example where
Sure.
So we're based on.
But there's no theorem stating that
the
locality and
no,
gradients and gradients implies this.
It will be. I think it will be like an hypothesis first. Yeah. So. Okay. So what I'm trying to do in this table I draw here is an overview of known results that do not use quantum information theory. And they are all based on studying properties of the stress energy tensor and somehow maybe using some dilaton to extract these properties or some other techniques. And as you can see, it's a very long program in the sense that it started, it's turning 40 next year. So, and there has been some interesting progress. And basically, what I'm drawing in the columns is small d, basically the dimension of the defect, and in the rows is, sorry, in this direction is big D, the dimension of the bulk. So basically when small d and big D are the same, you are in just quantum field theory, Lorentz invariant, and this is what I started by the proof of Samolov-Chico. And then people started to extend these results into several directions. So this is not a complete list of references, but I think it sort of gives you an idea on how things were moving during these years. And for the particular case of d equals 3, there are no proofs that, like, do not use quantum information. So what I will focus about is about entropic results of things that use quantum information theory. Again, the whole story started in 2004 with a paper of Cassini and Huerta, and then it was extended again in many directions. I won't be giving many details because it will be the main theme of this talk. The basic idea is that we will present an entropic proof for quantum field theory in d equals 2 to 4. It will be like a new proof unifying the results of Cassini and Huerta and Cassini, Teste and Torroba in different papers. And then we will extend this proof for the case of defects. And if time permits, I will tell you about what happens in ADS. That is some work in progress we're doing. So,
sorry.
Yeah.
The distinction between entropic and entropic proofs.
Yeah.
Why is this important? Could it be translated in some way?
I guess I just want to organize the results in a way that was useful to the presentation. But basically, the non-entropic proofs usually are related to properties of the correlator. For instance, Samolov-Chico proved like the positivity of the 2-point function and stuff like that.
Yeah.
And these things, I guess that in all the proofs, what you need is something that is well defined in all quantum field theories. And basically, T mu is always there. And here the idea is that, okay, you can chop a part of your quantum field theory and work with reduced density matrices in any quantum field theory. So somehow you can do it and get general results.
No, I understand that you're working using slightly different tools. I'm asking whether there is any importance in this distinction, or if there is a way to translate from one description to the other. Is there an advantage that you just look at correlation functions of local operators or local operators on the defect, or that you look at regions?
Well, I guess I have a few ways to answer this. The first one is that these have some quantum information interpretation, and you can sort of state it as losing degrees of freedom along the Archie flow.
But you would say the same for the usual proofs.
Yeah, but I don't know why the norm of the 2-point function measures degrees of freedom. If you don't like that one, I can say that, for instance, in 3 dimensions, these are the only available proofs that you have. And then
Again, I have nothing against what you're saying. I'm trying to understand how these two things relate to each
Ah.
other. You made this distinction.
And finally, at the endpoints where you have conformal maps and everything like that, you can map the charges in one proof to the charges in the other. That doesn't satisfy you.
Not really. Doesn't matter.
Okay. Yeah.
In the previous slide, you mentioned D equals little d equals 1, capital D equals 2, is Frieden connecting result.
Yeah.
In what sense is that not entropic?
Okay, so I was referring to quantum information, and that is like thermal entropy, right?
Yeah.
Sorry.
Okay.
Yeah, it was a bit of a loose
I see.
vocabulary. Yeah. Okay. Nice. So next, I will define what is entanglement entropy, just in case. Okay, I will. So basically, the idea is to consider your spacetime and take a sphere in it. That sphere will depend on the dimension of your spacetime, of course, but the idea it will be a codimension 2 surface here. What we will do is to build the reduced density matrix by tracing out the degrees of freedom living outside the sphere. And with that density matrix, what we do is to compute the von Neumann entropy, and this is what we call entanglement entropy. And the idea is that we will be able to probe the H flow by considering the limit of very small spheres where we will be in our UV, or very big spheres where we'll be like considering the whole H flow, but somehow we will be able to extract information about the IR fixed points. So at these fixed points, the structure of the entanglement entropy is well known, and it has this form that I'm writing over here. It basically starts with an area law, and then you have subleading contributions, and eventually you reach to either a logarithmic part or a constant part, depending on which dimension you are living on. And the coefficients appearing here are what are so-called universal coefficients, and are the ones that are good candidates to be Archie functions. So basically, okay, and referring to the comment I was making, when, for instance, you compute the partition function in the sphere, you can read these coefficients as well, or when you compute the Weil anomaly in even dimensions. So these are the guys we will try to read from our entanglement entropy. And as you can see from here, they are subleading with respect to these guys. And basically, these things are the ones spoiling the theorems in higher dimensions. So basically, getting to the things that we want to read is harder and harder when we go up in dimension. That's why we cannot prove irreversibility in dimension higher than 4. So, now if we turn on the Archie flow, the entanglement entropy will be way more complicated, but maybe a way to parameterize this is to imagine that these coefficients appearing with the area law and the subleading part and the universal parts now have a dependence on the radius. So I should have said here that the thing that makes these things adimensional is the fact that this mu to the mu sub d minus 2 depends with the cutoff like epsilon to the d minus 2, so that this thing doesn't have any dimensions. Okay. So basically, when we turn on some relevant deformations, we can make these things arbitrary functions of the radius by adimensionalizing it with the mass, scale that we introduce. So, okay, that being said, since we want to read these subleading coefficients, one thing that we can construct is, for instance, this quantity I call here C of R. That will be our C function. And the idea is that it basically has two distinct behaviors. When d equals 2 is just the derivative, and the derivative of the logarithm is just 1 over R, and this gives you the A that in 2 dimensions we call it C.
Question?
Yeah.
Away from the fixed points, what guarantee that you're not going to have R to the d minus 3, say, for terms? Is that it's going to drop again by 2?
I guess you can hide it in the parametrization here. And this is just some qualitative feature, like just imagine what are C functions. Yeah, thank you. I mean, this formula should not be an equal here. It's like some sort of interpretation thing.
What is the epsilon?
Epsilon is the cutoff. The?
Epsilon. What is the epsilon in the formula law?
Yeah, this is the UV cutoff.
What?
The UV cutoff of the theory.
Cutoff.
Yeah. Okay. Okay, perfect. So basically, what this formula does is when you apply it to the conformal fixed point, to the fixed points, it reads the universal part of the thing. And then away from the fixed points, okay, it has some non-trivial radial dependence, but it will interpolate between the central charges or archy charges of the theory. So basically, once we have this thing, what irreversibility means is to consider that it decreases as we increase the radius of the sphere. So we get to this formula, and proving this formula in the different setups will be the goal of this talk, or generalizations of the formula. Okay. That being said, I will proceed to prove the formula. So if you have any questions about general setup.
So in a different set of topological orders where you have this as an edge mode sort of distribution, there have been proposals of how to extract that piece by considering different configurations of different subregions. Is
Yeah.
there such a...
Like the Kita F thing, you mean?
Sorry?
You mean like the Kita F?
Yeah, exactly. Is there a similar thing for CFTs that, broke through?
Well, I guess the main thing is that we are kind of trying to look for non-topological degrees of freedom here.
Yeah, but still the universal degree, you want to extract the universal piece.
Yeah.
Saying if there's a configuration of different regions that extracts this C function.
Yeah, there is, but you won't be able to prove the monotonicity of that thing. Okay, perfect. So the way to make the proof is basically to consider an entangling surface sitting on the null cone. So the fact that it's sitting on the null cone means that times is equal to the modulus of space, and you can draw whatever curve you want in the null cone. This curve will be like the ends of this ice cream cup, and basically your entanglement entropy will depend on this curve that you choose in the null cone. And the idea is to consider infinitesimal arbitrary null variation of the entanglement surface around some particular surface gamma that we will eventually take to be the sphere. And okay, so basically what we can do is do some Taylor expansion, doing this, defining these kernels that are variations of the entropy with respect to variations of the curve, and integrating them over the angular coordinates. And what we recognize at second order in the variations is the main character of this entropic proofs, that is the strong subadditivity. So strong subadditivity, what it's saying is that the off-diagonal part of the kernel must be negative. So basically, if I take this thing and I integrate it against some positive vector, I will get some negative number. Great. So, and this strong subadditivity is a general property of entanglement entropy, and it will be quite helpful for us. I mean, we want to prove some inequality, and this is the thing that will provide us the tool. So the two key points, as I was anticipating, was to have something that is negative or has a definite sign, and then Lorentz invariance. And so what we will do is to understand what are the implications of Lorentz invariance on the entanglement entropy. So to do that, what we will do is to consider some curve on the null cone, and then boost it so that the total length of the curve or the radius of the sphere doesn't change. And what we will do then is just take the not boosted interval and the boosted one, and requiring that the entropy doesn't change will give us some relations order by order in the Taylor expansion I defined before. So basically, plugging the expansion for a small boost into the formula I showed before, what I find is this relation I write over here. Basically, that the angle integrated against the kernel of the subadditivity should be equal to this other vector, this other function I have here, integrated against the first order kernel. So, with this thing over here, I can simply try to think what this formula means, and then basically what I have to do is replace this formula by defining a first derivative as the integral of the first variation, and the second derivative as the integral of the second variation, and simply by playing a little bit with the expressions I got before, I get this nice formula that basically tells us that this kernel that we knew to be negative, when integrated against this vector that is definite positive because it's 1 minus some angle, is less or equal than 0. So, in order to be sure that we don't have any U diversions spoiling our thing here, because this is true only when gamma 1 and these two variations are different, we need to further regularize the kernel by considering, instead of S, the difference between the entropy in the whole theory minus the entropy only on the fixed point. And this entropy in the fixed point, what happens to satisfy is that it saturates this inequality. So basically, inside this kernel is just 0. So basically, we can safely plug delta S instead of S in this formula. And then we have something that is UV finite, or at least better behaved, and that's how we finish our proof. Yeah.
Sorry, what's the mechanism that allows you to write a first derivative as second derivative? Like you have S prime of R, and then on the right hand side you just have second derivative.
Yeah, thank you. Is Lorentz invariance. Basically, what it turns out to appear there is just this combination of vectors, and then I flag. I mean, you have to play a little bit with tensor structure, but it turns out to be that. Yeah, thank you. So this sort of proves irreversibility for QFTs, and what I'm going to do next is to move to CFTs with defects. So if you have any questions, it will get a bit harder. But yeah.
Looks like naively you're mixing different orders in the perturbed expansions.
In the Lorentz expression, or?
Yeah, I thought you, a few slides back, you mentioned asking some sort of Taylor series, and here it looks like you're mixing different orders. What?
Oh, yes, thank you. Because you have a contribution coming from the first order expansion of the curve that you can plug it twice, and that's how you get one of the contributions. And then you have this thing that has already order 2. So that's how they mix. Was I clear now?
I don't
So basically, what we did is in this expression replace this delta gamma by its expression in terms of changes when you make a boost for small boosts, and that's okay. Yeah.
So here it's the context of Lorentz invariance in the repeated version, so it's positional invariance.
No, it's Lorentz.
So
Yeah.
So the sphere is the spatial sphere.
Basically, you have the sphere, and it's no, I mean it's causal development. I think if you move away from spheres, you cannot say many of the things that I said. So it will be very from spheres. You cannot say many of the things that I was saying. So. Was that your question? Or? So, equality. Defects. So the idea about defects, I will have to go a bit fast now. Is to consider again a sphere that lives in your bulk space-time that was big D dimensional, a codimension 2 sphere basically, and then to put the defect in such a way that everything is maximally symmetric. So it cuts the thing through maximal circles, and then what you get is some the way you break the rotations of the sphere is in the minimal possible way. Let's say it that way. So, I mean, you can consider, for instance, if we were in 4 dimensions and the defect was 3 + 1 and was the blackboard, what I would have to do is to consider a sphere that is just or half a sphere that is a maximum circle of the sphere touches the green board in this case. So that is the idea. So because if you consider some other configurations, all the dependence will be on the geometry will be much difficult. But with this setup, and close to fixed points, we have a very clear understanding of how the entanglement entropy looks like. And it's a bit overwhelming, but it should not be. It's basically the combination of untilted quantities that goes like the bulk entanglement, and tilted quantities that goes with like the defect entanglement. So basically, you have an area law that goes like the area of the intersection of the sphere with the defect. And then again, you have universal contributions, tilted and untilted ones, and you will be interested on the tilted ones that are the ones related to the defect. So with this in mind, we could in principle believe that we have everything we need, but there is a problem that we already know that this entanglement entropy does not read the correct Archie charges. And this is because the defect has some energy and it ruins the monotonicity of the entanglement entropy. So what I will do next is to explain why this happens and then to show how to fix it. So basically, the first thing to notice is if before we had things ruining or hiding our interesting terms that aren't these ones, now we have many more things. But luckily for us, there is a simple way to get rid of all the untilted quantities coming from the bulk, and it's just by subtracting the entanglement entropy associated to the UV fixed point. So in this way, the UV fixed point also has the defect. So it basically, this delta S, what it does is it defines something that already measures the difference between the IR charges and the UV charges. So basically, in the limit of large spheres, you get this expression for delta S, and so basically we got rid of a lot of the things that were bothering us before, but we still have some other problems. And the other problem I anticipated was the fact that as the one-point function of the T mu nu of the theory with the defect is non-zero, while it was zero for non-defect CFTs, your entanglement entropy, the logarithmic part of the entanglement entropy has two contributions. One we call delta B, and one we call delta D2. And what are these things? Well, in particular for D, small d equal 2, so line defects. No, not line, surface defects, sorry. You can compare, for instance, with the coefficients appearing in the anomaly, and basically the trace of the T mu nu in the defect theory has a contribution that goes like the Ricci scala, but also has some other anomalous terms coming from, you know, like some extrinsic curvatures and the induced Weil tensor on the defect. So this thing is what it is known to be a good Archie charge, and these things are contaminating our entropy, in particular this one, the D2. And this D2 comes from the fact that the bulk stress tensor has a non-trivial dependence on the distance with the defect, and basically you can read it from the bulk stress tensor. Okay, so basically we cannot use entanglement entropy, but instead what we do is to use relative entropy. And what is the relative entropy? It's something that you have to consider two states, and it will give you a number. Basically, it's defined as follows. But there is quite an enlightening redefinition of the relative entropy that we can define it as the difference of the expectation value of the modular Hamiltonians minus the difference of the entanglement entropy. This is quite enlightening because we work a lot with the entanglement entropy and this object, and the idea is that this modular Hamiltonian will be related to the stress energy tensor, and it will fix the problems that the entanglement entropy had. So in the context of these irreversibility theorems, we will choose this relative entropy to compare a state that will be the reduced density matrix of the complete QFT with the relevant deformation and so on, and sigma to be the reduced density matrix of the fixed point. Notice that this thing is not symmetric when changing rho and sigma, so it's important which one is which. Good. So what I will do in this slide is to briefly tell you that for when we choose sigma to correspond to a DCFT, we know what is the modular Hamiltonian, and it's built in terms of the stress energy tensor and two vectors, psi and eta. Basically, this psi here is a Killing vector associated to conformal transformation that lead the sphere its place, and this eta is a unit vector normal to the Cauchy surface that we are choosing. So basically, our recipe has one last input, that is the choice of this Cauchy surface sigma, and the choice that gives a sensible answer for the question that we are making here is to consider this sigma to be a null surface, like towards the future, or the past is the same, of the causal development of the sphere on which we are measuring the relative entropy. So this is because the way divergences appear depends on the choice of sigma, and for non-sigma, the divergences we get are comparable with the divergences we get for the entanglement entropy. And after some computations, what you actually get to see is that the structure of this relative entropy around our fixed points is just the same as the structure of entanglement entropy. Basically, it has some RLO, it has some leading terms, and finally you get to the Archie charges here. And when you take, for instance, a conformal field theory and see what are these Archie charges, they actually measure the delta V associated to the, for instance, to the partition function of the sphere. So, sorry for this, I mean, few slides, but the prescription to read the correct Archie charges is not that simple in defect CFTs, but now we have it, and we can see what can we do to prove the monotonicity of the Archie flow. So this relative entropy has some nice properties. For instance, it's positive and monotonous when we increase the radius of the sphere. So if your Archie charges are close enough to the leading part, for instance in d equal 2 or in d equal 1, small d I'm referring, then you can directly read from the relative entropy from the positivity of the relative entropy, you can actually prove that the Archie flow is monotonous because it directly reads the universal terms. But if you're willing to go beyond equal to, you have to use something else, and that something else is the strong superadditivity. That basically, when you are considering spheres, just as entanglement entropy had the strong superadditivity, relative entropy also satisfies something like this. This is something associated to what they call Markov property of the vacuum, and it was proved in this paper. We basically, with this ingredient, we can build differential inequalities out of the relative entropy. So the last thing I will have to show is a bit orthogonal to what I was saying until now. So if you want to ask some questions, or did I lose you already?
Is there an easy way to understand why you need more if the dimension is higher, dimension of the defect is higher?
Yeah, because when you're in d equal 1 or d equal 2, these things don't appear, and you start your expansion directly with the Archie charges. And then when you move higher up in dimensions, these things spoil your proofs, right? I mean, you can prove that this coefficient is, or maybe this coefficient is monotonous, but it doesn't tell you anything useful. Or maybe it does, but we don't know what it is. So, any further questions? So, basically, the last ingredient we need to add to have all we need for the proof is the quantum null energy condition. And this quantum null energy condition, what is referring to? It has a long history. It's related to the focusing conjecture in gravity, but for our purposes, all we need to know is that it's a positivity statement of the relative entropy when you deform null surfaces. It was first introduced in Rindler, and basically when you do a small deformation around the Rindler wedge with some positive parameter, you can prove that this the second derivative with respect to this parameter will be greater than 0. And then you can formally map the Rindler proof to show it for quantum field theories living on cones or on spheres. And basically the statement is that it improves the strong superadditivity of the relative entropy by now allowing deformations where the curve coincides, where the deformation of the curve coincides in the points. Basically, okay, so this improvement over here is only valid for CFTs because you have to do some conformal mappings to prove it. But we will only use it away from the defect, where and since our bulk is still conformal, it's okay. I mean, we can use it as far as we don't use it on top of the defect. So the last step to conclude the proof is to grab this thing now using relative entropy instead of entanglement, and plug it in the Taylor expansions that we had defined for for variations of the relative entropy with respect to the curve. And what we notice is that this thing is just equal to this other thing, but what appears here is actually the kernel associated to the QNIC. So that's why it was important. So away from the defect, the theory is conformal, so QNIC is valid, and this thing is always positive. At the defect, we don't have QNIC, but this thing is the non-local part of this thing is still positive, and when you take x1 equals to x2, you get a 0 here, so it sort of fixes everything, and then just this concludes the proof. Basically, we managed to prove that this thing is greater than 0, and then plugging case by case the different dimensionalities, we get to see that each of these differences defined between RG charges have a definite sign. And as I was, actually you were anticipating, when d is greater than 4, you don't get to constrain these terms over here, but you think that we don't know exactly what it is. So I guess this concludes the proof for defects. So, and I still have 10 more minutes. So if there are not any other questions, I will show you something about ADS. Yeah.
How do the A prime and F primes relate to the known defect central charges that do decrease under RG flow? You mentioned that they map.
Yeah, the numbers are in front of everything are fixed in a way that they are exactly. I don't know. If you take b equal 2, you get the b defined by that Shenzhen and Oban studied and so on. If you if you plug the equal 1, you get Frieden and Konechny.
And is there any interpretation of what these are for d equals 3, where there aren't results?
I think, yeah. I mean, they are related to the constant part of the free energy on the sphere, but you don't have any tools to prove that thing is. You don't have any other tools to prove that that thing is monotone.
I see. Okay.
Yeah.
Can I apply the opposite logic? So if you assume that the theorem works as we expect, that these things are monotonic in any dimension, can you derive higher order constraints under relative entropy?
Yeah, you can actually do that. Yeah. But are you asking if they are interesting or?
Yeah, if they're true.
Yeah. The thing is, it's usually very difficult to actually compute the relative entropy. So, for instance, for holographic theories, I think the only examples we know are holographic theories. They work. So.
No, I was asking if there is maybe some quantum information. I mean, if you can see that this emerges from some general principle.
It would be very nice, but so far there are no results in that area. Yeah.
Could you separate the deformation in this relative entropy away from the defect for quantity? It looks like this global quantity is defined for some unit radius of the sphere. What did you use to
That. Can you repeat the question, sorry?
A few slides ago, when you were applying the QNEC, you said you only needed to apply it away from the defect.
Yeah.
This entangled entropy, it looks like a global property of the whole space. It depends on the radius. How do you?
What I meant is, okay, I have to do this integral over the whole entangling surface, and that entangled surface will eventually touch the defect. So I know that this kernel is positive away from the defect. But when it touches the defect, I have this vector that it goes to 0. So I don't care if this thing gets negative just in the defect.
Before you also did some subtraction where you removed the contribution from the bulk method. Is that?
Yeah, the subtraction I did before, it was okay. The relative entropy implements it naturally, but it was to compare the relative entropy of the whole arch flow with the relative entropy of the UV fixed point. So it's not that I'm cutting away the defect, but I'm considering the UV fixed point that it actually has the defect. But the nice thing is that all the bulk parts, as the bulk doesn't flow, they are the same, so they just cancel away. And
so why is the integrand just strictly 0 away from the defect?
which integrand?
It's integrand of your variation of S well.
Why isn't it strictly? Because it still has some. It still has some dependence on the fact that you have the defect. So you don't have the full conformal symmetry, but just that the divergence structure is just the same as the one associated to the QFT of the defect. So what I mean is, even if the trace of the T mu is exactly 0 away from the defect, it doesn't mean that your theory is conformal, right? So that difference is what makes this kernel over here to be non-trivial. Yeah.
So usually we distinguish the non-universal term from the universal one because they are cutoff dependent, no?
Yeah.
But here this the relative entropy is fine.
So yeah, exactly. It's fine.
So why do you still call this term non-universal?
Yeah, maybe it's an abuse of language in the sense that we don't know what it is. I mean, it would be nice to have a good interpretation of its meaning. For instance, the area terms are supposed to be associated with the flow of the Newton constant. These subliving parts, I don't think you know exactly what.
Isn't the point that if you rescale the cutoff, they will change, right? They're not universal in that sense.
No, but I think what he's saying is, since this quantity I define here is UV finite, then there is no actual distinction. I mean, this is UV cutoff independent quantity. But still what we want is this universal parts. These things that go like logarithm, because are the ones that we know what they mean in quantum field theory.
But maybe I understand Giuseppe's point. So this quantity that you wrote there, delta mu prime, these are not cutoff independent, right? So how can that formula?
These are cutoff independent. This thing is UV finite. It's a bit.
What sets the scale? What sets the scale in that case then? If they don't depend on the cutoff?
And R has dimension, so what's the scale?
Because you're comparing, when I define it, I was comparing something that had a QFT with the CFT1, and all the dimensions come from the QFT part. So basically the mass dimension that you added to the QFT is playing the role of the cutoff in the CFT.
But all of these delta mu's have dimension. I don't know that they have to, right? Because R has units.
Yes, but the dimension comes from.
Yeah.
So, I'm in red numbers now, but as you can imagine, as you will have to imagine actually, since ADS is a maximally symmetric spacetime, we can now consider QFTs living in ADS and wonder if all these things apply apply now that I consider a QFT in ADS. So in principle, you have sufficient enough isometries to make the work. So the very short answer is that you get defining this big R going like the tangent of theta 0, with theta 0 being the coordinate of in global coordinates of the endpoint of the sphere. What you get is a very similar formula to the one that we had for Minkowski. It's actually the same formula, just that the ugly part is hidden in the definition of R. And so we can actually prove a monotonicity formula. But what we are not very sure is what does it mean, if it has any implications in the context of ADS-CFT, because in principle we are just considering QFT in a fixed ADS, just like Birren and Davis sort of computations. But it would be nice to have something to make these things mean something in the context of ADS, and actually to do some explicit computations, because we don't have many explicit examples of entanglement entropy in quantum field theory in curved backgrounds. So that being said, I was explicitly asked to leave some open questions. Many of those you already anticipated, like, for instance, what happens in higher dimensions. Another thing, it will be interesting. I was always speaking about defect archiflows, but what happens when I turn on relevant deformation now in the bulk? What is there a notion of irreversibility in curved spacetimes, and what does it mean? And then defects break Lorentz invariant in a very controlled way, but more general breaking of Lorentz invariance is known to be very difficult to address, and in particular there are things that people call boomerang archiflows that seem to contradict the notion of irreversibility. So it would be nice to push further this program in all these directions. So that being said, thank you very much.
Questions?
Sorry, can I go back to the question about universality? So I still don't understand, because we know at a fixed point, this cannot be universal, right? Because there is no scale at a fixed point. So what happens to this delta mu when you go to the ER?
Okay.
Like, I mean, what I'm saying is, like, you're saying these are universal objects, right?
Yeah.
They don't depend on the cutoff. But then what happens when you go to the AR, where we know they are not universal, right? At the fixed point.
Which objects you're talking about?
Delta mu prime.
So delta mu prime in principle is not the same thing as the one in the entropy. So
well, it's the difference between the one you have at the UV and the one you have at the IR, right?
yeah. So you're asking me if you. Yeah, but
so you're saying the step. Okay, you're saying is it the delta important, or is it the fact you're looking at the relative entropy and then makes it universal? Is that what you're saying? So
okay, so
is the delta doesn't do much, right? It's just the difference with the UVs.
But basically, when you fix the cutoff in the UV, and you cannot, I guess what is saying this thing is that you cannot choose a cutoff in the IR because the UV and the IR are connected by the Archie flow. So in that sense, they sort of became.
But you wouldn't want to choose any cutoff, right? You're saying this is just independent of the cutoff. even in the UV, or
No, in the UV these things
are 0.
Is 0, yeah, exactly. So probably what is confusing you is this delta is not the difference between the IR theory and the UV theory, and then.
Well, when you get down to the IR, it is.
Yeah, but sort of connected via the R sheet. So now all the cutoffs are the same, and that's how it sort of makes sense, the quantity.
I don't know, I'm still confused because there is no cutoff, right? You start from something where this delta mu is 0, you flow down to the IR. What is it in the IR?
Yeah, it's some number.
But
3.
you said this delta mu needs to have dimension, right?
Ah, yeah, you're right. So it's 3
There's
times
no scale.
the mass of the.
There's no scale in the IR.
Okay, but when you're in the IR, your mass scales that you put into the theory now play the role of the cutoff, right? Because you're integrating out everything that is below that scale. So
then it will depend on this cutoff.
Okay, yeah. So, but it's dynamically defined, right? It's not something that you're putting from the outside.
Well, all I'm saying is that if I have a massive object and I do RG flow, I know very well how this object scales, right? Because if it's massive, so either it's relevant or it's irrelevant. It's not. So, is that all these equations are saying? Like, if a massive object, so if I do RG flow, it's gonna follow the flow according to whether it's relevant or irrelevant.
Yeah, I'm actually assuming it will be relevant. So yeah.
Can we say it's non-universal in the sense that it depends on how you arrive at the IR?
Yeah, I agree with that interpretation.
Of the fixed point, but of the flow itself.
Yeah.
Yeah.
Yeah, thank you. I agree with that.
Any other questions? Maybe something related to what Status asked earlier. Like, so far you've used Vonnegut entropy and relative entropy, but there's like a plethora of different measures, right? And is there some intuition for like, why these two? I mean, in this case, gives you some measure of degrees of freedom versus other.
No, I guess probably many of the plethora of interesting measures will give you something interesting, but it's very hard to have like powerful tools like transadditivity for any measure that you choose. So that's what I think what's actually constraining you choosing these things.